Before you start watching, I should warn you that it may be hard to grasp some moments straight away, so I invite you to pause and ponder anytime you feel you need it. There are also text fragments in the following steps that provide the same content as the video. You may read through them instead of watching the videos if you find that format preferable. Let's look at the toTfunc function defined in another lesson. Notice that this res function within the body of the toTfunc function is kind of redundant. We'd like the definition to be more compact. The same is true for this multiply function that requires all the syntactic constructions despite its simplicity. To avoid writing def explicitly, we may use the anonymous function syntax. To create a function in this manner, we use the lambda keyword. Enumerate through comma all the parameters, then write the expression that is the body of the function after the colon symbol. For example, we could define the multiply and add function like that. Or we could avoid creating a redundant function in the toTfunc body like that. We may even use such a definition twice. This way we create a function that, given the argument f, returns a function. This syntax may be used to reduce the number of arguments a function takes by explicitly specifying one or more arguments of the function in its body. You could also make use of stacking multiple lambdas to create a function that takes each of its arguments separately. That is, each time you provide a single argument and get back a function with effectively less than bound parameters in its body. I'd also like to mention that many find that this lambda keyword an awfully long one to write. It really clutters up the screen pretty fast. An alternative syntax may be found in the fn module. You can see the example here. Basically, each underscore corresponds to a separate argument. It is said in documentation that this syntax is Scala-like. I avoid using it because an underscore is strongly associated with the designation of a redundant argument of a function for me, the so-called wildcard. But I guess some of you may find it much more pleasant to write using this notation. I also recommend you to look at FNPY documentation on GitHub in general. It is a model designed to make functional programming in Python more simple. However, I will not go into details of what you may find there. Now, recall the next square function. We may write it in a functional way without actually defining all the functions and use an anonymous function instead due to the simplicity of the functions we need. But we could also choose another way to do it. Notice that it's kind of redundant to write the argument in the function's body in this case. I mean, yeah, we define a function in terms of how its result depends on its arguments. That's true. But when we define this next square function, it's not this dependence we're trying to express. We want to say that to get the next square, you take the square root first, then increase, then raise to the second power. In order to concentrate on this meaning on the function, we could use composition. Composition of functions f and g is a function h such that given some arguments, h returns the result of applying g to these arguments first, and then f to the result. Notice that when we say that h is a composition of f and g, we don't need to specify explicitly what does it do with the given arguments. We fully define a new function h in terms of the ones we already have. And when we're making things in a functional way, we have a lot of pre-made small and general functions to use as some kind of building bricks for more complex ones. Thus, having a tool for this composition method would probably be quite useful. We could define a composition function by ourselves, but there's no need in that, since there is one already in the Python tools module. Using this compose function, we could define the next square in a really straightforward way. The only thing to know here is that, of course, the order in which you compose functions matters. The last function is in the composition chain will be applied first, and so on. By the way, this method of defining a function without writing its arguments as a parameter within the body is called a point freestyle. It's commonly used in functional programming. The last thing I wanted to show in this lesson is an example of the connection between the mechanics of anonymous functions and the origins of the Lambda expressions. You've probably heard about the Turing machine, an abstract model of computation developed by Alan Turing based on the idea of evaluate a change in its state as it's processing some data storage by performing some operations on it. The storage is usually described as an infinite tape. There was another model called Lambda calculus developed by Alonzo Church. Unlike the Turing's model, the Lambda calculus there is no strict distinction between data and operations. That is, we may represent data as functions, and we can manipulate functions as if we were manipulating data, so data and operations are homogeneous. This model is at the heart of the programming languages that are considered to be functional, like Lisp or Haskell. Some of these concepts enable programmers to do so much more things that a lot of languages adopted some of them. You already know the ability of passing functions to the other functions and returning functions from other functions in Python. So this manipulate functions as if we were manipulating data is quite clear. But what's that we can represent data as functions? I want to show you this system called church numerals. It's about using lambda expressions to represent numbers. Let's define number n to be a function that takes some input f and returns another function that is effectively a composition of this f function with itself n times. That is, given x, it returns f applied to x, then f applied to f of x, and so on for n times. Thus, 0 is a function that, given any function f, returns an identity function, which just returns its arguments. It's the same as returning the argument with function f applied to it 0 times, and so on. Now, how do we get the next number given number n? Since any numeral is a function that takes some function f and returns another function that's composition of f with f made n times, then, given such numeral n, to return the next one n plus 1, we should return a function that, given some function f, will return another function that is the composition of f made n plus 1 times. But that's actually a composition of f and n as a numeral. So we need to return a function that, given f and then x, will return the same result as n numeral, but with f applied to it for one more additional time. To check if it works, we may test it with a concrete f and concrete x. That will make it more clear. The most convenient example is having 0 as x and the increment function as f. First, let's test our numerals. Now let's find the result of applying f and then x to the numeral that's the successor of 3. It actually works. I want to point out once more that these are the functions that are numerals, and not the result of applying some particular f and some particular x. The latter is just a way to represent the numerals. We may prefer some other representation. Now, let's think of some way to perform addition and multiplication of such numerals. Well, addition should be a function that, given numerals m and n, returns the m plus n numeral, which is a function that, given some function f, returns another function, which is the result of composing f with itself for m plus n times. Thus, given some function f and then some argument x, m plus n numeral will return the result of consequent application of f to x, then f to f of f at x, and so on for m plus n times. But this is the same as applying f to x n times first and then applying f m times to the result. Thus, if we give n of f of x as the argument to m of f, we will get exactly what we want. Let's check if it really works the way we expect and proceed to the multiplication function. Once again, multiplication function should take numerals m and n and return a numeral m times n, which is a function such that given some other function f, it returns the result of composing f with itself m times n times. Notice that if we give to the m numeral not the f function, but the n of f function, then we get a function of x. Given x, this function will apply n of f to x m times. But what does it mean to apply n of f to x m times? Well, n of f is a composition of f and f made n times. To apply it once to some x means to apply f to x n times. To apply n of f twice to some x means to apply f to x n times, then n times again to the result. That amounts to 2 times n times of applying f to x. Thus, if we apply n of f to x m times, we apply f to x exactly m times n times, which is what we want. Let's check if it actually works. Usually, Boolean values are not numbers, so it's not a satisfactory solution to represent Booleans as numerals since we've implemented the latter. Here's an implementation of Boolean values as functions. How does it make sense though? Well, we may intuitively understand it if we represent each functional Boolean by applying numbers 1 and 0 as x and y. Okay, but it's all about being able to operate on data. How do we implement common logical functions? Let's make an AND function. It's not that complicated actually. An AND takes two such booleans, b1 and b2. If the first one is true, then the result should be whatever the second argument of AND is. Otherwise, the result is already defined to be false. Then AND may return the application of the second argument and then the first argument of AND, in that order, to the first argument itself. This way, if the first argument of b1 is true, b1 will return its first argument, which is the second argument of the AND function. Thus, AND will return its second argument. If b1 is false, it will return its second argument, which is b1 itself, which is false. And that is exactly the desired behavior. Another function to make is NOT. Well, if the value that function represents depends on which of its arguments it returns, flipping the order in which the provided arguments are applied switches the Boolean value of the function. There's a lot of other things you may do with it, but that's it for this lesson. If you feel curious and adventurous, you may try to learn some more things about lambda calculus and usage of combinatorial logic in programming. These are more advanced, theoretical heavy topics, but you may find them worth exploring.